Welcome folks, a video today on dimension. So in this video we'll define the dimension of a vector space, we'll identify the dimension of several different vector spaces that we've been looking at. We'll talk about characteristics of a matrix that have to do with dimension of certain matrix subspaces, and then we'll talk about those characteristics as they pertain to a non-singular matrix. So here's a definition of dimension. Suppose that a vector space S has a vector space V has a basis S. The number of vectors in that basis is called the dimension of the vector space. If there isn't a finite basis, we say that the vector space is of infinite dimension. Okay, so the take-home message here is that to figure out the dimension of a vector space, count the vectors in the basis. Here's the theorem I'll state without proof. Suppose that you have a spanning set, V1 out to Vt, for a vector space V. Then any set, say that set is T, with more vectors than V, must be linearly independent. Okay, so more vectors than is needed to span must be linearly dependent. Here's an example. We previously saw that this set of 4 vectors is a basis. That is, it spans and it's linearly independent in W, the set of all quartic polynomials where evaluation at 2 gives 0. So here are 5 elements of W. These are all elements in W. And by our previous theorem, since there are more elements in this set T than in a spanning set for S, for a spanning set for W, then the set T must be linearly dependent. Okay, so again, more elements in T than elements in a set that spans W, therefore T must be linearly dependent. Okay, suppose that we have a vector space with a finite basis B and a second basis C, then B and C have the same size. So this is sort of a pretty cool proof that uses some ideas of contradiction. So we begin by assuming that the basis B has M elements and that the basis C has N elements. So with those bases B and C, we'll assume toward the contradiction that M is greater than N. Well, we know that C is a basis, and if C is a basis, it spans the vector space, right? A linearly independent set that spans is a basis. If B has more vectors, it must be linearly independent, which would be a contradiction of it being a basis. The same argument works assuming toward the contradiction that N is greater than M. If we assume N is greater than M, then the fact that B is a basis and spans V implies that C is linearly dependent, contradicting it being a basis. So the only conclusion, therefore, is that M is equal to N. Okay. So this is sort of a good thing. This is a result of the fact that more vectors in a set than a spanning set is linearly dependent. Okay, so let's talk about the dimension of a few familiar vector spaces, and in order to do that, all we'll have to do is identify a basis. So here's an example. The dimension of the vector space of column vectors is M. Okay, similarly, the dimension of the set of all polynomials up to and including degree n is n plus 1, right? And we can see this by writing down the standard basis for this polynomial vector space, just like we did for the vector space of column vectors. Okay, and finally, the dimension of the vector space of M by n matrices is M times n, right? So we've seen this before too. A basis for that vector space, M2, 3, for instance, would be the 6 2 by 3 matrices where there's a 1 in a row and a column, and zeros elsewhere. Here's one I'll let you work out. Let's go ahead and find the dimension of the subspace of 2 by 2 matrices defined by these two conditions. Okay, so I'll let you work this out on the worksheet. And what you should find is that the dimension of this subspace is 2. Okay, and the way you do that is by constructing a basis for this subspace. We were just looking at this set of vectors W that are all the quartic polynomials with polynomial evaluation at 2 equal to 0. We saw a linearly independent set that spans this subspace. So with these 4 elements is a linearly independent set that spans W. It's a basis of W, so the dimension of W is 4. Similarly, we saw a linearly independent set that spans the crazy vector space. Okay, the set 1, 0, 6, 3 is a linearly independent set that spans the crazy vector space. It's therefore a basis, so we see that the dimension of the crazy vector space is 2. The set P defined by the set of all polynomials has infinite dimension, and to see this, we can use a contradictory statement assuming that it has a finite dimension. Okay, if we assume toward the contradiction that the dimension of P is n, we know that the set 1, x squared out to x to the power n is a linearly independent set in P. It has n plus 1 elements, which contradicts the assumption of finite dimension. So here's an example of an infinite dimension vector space, a set of all polynomials. Okay, let's talk about characteristics of a matrix, rank, and nullity. So here are a couple definitions. If A is m by n, the nullity of A is the dimension of the null space. Here our notation n of A, dimension of the null space of A. Similarly, when A is m by n, the rank of A is the dimension of the column space. If we want to get the nullity of A, we can apply theorem BNS, right, the basis of a null space. So start with A, reduce it to its reduced row echelon form. We know how to identify a linearly independent set T such that the span of T is equal to the null space of A. And then the number of vectors in T will be the nullity of A. And it's similar for the rank of a matrix. Okay, to get the rank of a matrix, we'll apply theorem BCS, right, the basis of a column space. That is, take A, reduce A to reduced row echelon form, identify a linearly independent set S such that the span of S is a column space. And then since the rank is the dimension of the column space, we know that the number of elements in S is the rank of A. Okay, so I'll have you work out the rank and nullity of this matrix, this 6 by 7 matrix on the worksheet. So go ahead and use some software to do that, but here's what you should find. What you should find is that the reduced row echelon form of A has 4 non-zero rows. Theorem basis of null space tells us that there are n minus r, in this case equal to 3 elements in the basis of the null space. Theorem BCS tells us that there are equals 4 elements in the basis of the column space, so the nullity of the matrix A is 3, the rank of the matrix A is 4. Okay, so that thing we've been calling R all along, that's the same R, right? The number of non-zero rows in a reduced row echelon form ends up being the rank. Okay, and it's always true that the rank and the nullity sort of change size inversely. So that's the theorem when A is m by n and B is the reduced row echelon, the matrix in reduced row echelon form. With R pivot columns, then the rank of A is R and the nullity of A is n minus R. So the proof of this is exactly the two theorems that we just identified. Okay, theorem BNS tells us that there are n minus r vectors in the basis of the null space. Theorem BCS tells us that there are vectors in the basis of the column space. Hence, the nullity of the matrix A is n minus r, and the rank of the matrix A is r. It's pretty quick now to see that the rank plus the nullity is always the number of columns. Okay, again, the rank of a matrix is r, the number of pivots in the reduced row echelon form. The nullity of a matrix is n minus r, and the rank plus the nullity is the number of columns. Okay, let's talk about rank and nullity of a non-singular matrix. Here's an example. This matrix E is non-singular. Non-singular matrices reduced to the identity. We can see that this matrix is 7 by 7. Therefore, in its reduced row echelon form, it has 7 pivots. The rank is 7. The nullity, it turns out, is 0. Okay, and it turns out that this is always true, that for any non-singular matrix, the rank is the size of the matrix and the nullity is 0. So that's a theorem. The following are equivalent. A non-singular, the rank of A is n, the nullity of A is 0. And the proof is pretty quick. A is non-singular if and only if the reduced row echelon form of A is the identity matrix, if and only if the rank of A is equal to n, if and only if the nullity of A is equal to 0. Okay, so I'll point out that we sort of identify the trivial null space as having dimension 0. We talked before about how the 0 vector is a trivial subspace of any vector space. So in this case, the 0 vector is a trivial subspace of the vector space of column vectors with n components, right? So the dimension, again, of that trivial subspace is 0. Okay, so this is one more addition to our non-singular matrix equivalencies. The rank of a non-singular matrix is n, and the nullity of a non-singular matrix is 0. Okay, folks, hope you've enjoyed this video on dimension. Pretty straightforward concepts here. Dimension is the number of vectors in a basis. A dimension may be infinite, and we saw how the characteristics of a matrix, the dimension of the null space and the dimension of the column space, sort of vary depending on the number of non-zero rows in the reduced row echelon form of a matrix. Have a great day, and we'll see you next time. So long for now. Bye-bye.